You ever notice how an animal can get hurt and, just limp away? But a robot just breaks. It's done. So what if we could change that? What if we could give robots that same kind of resilience? Well, some incredible new research is doing exactly that. And today, we're going to break down how they're training smarter robots that can adapt when things go wrong. It's pretty cool stuff.
So, here's how we're going to tackle this. First, we'll get into why robots even need a variety of moves. Then, we'll look at this awesome idea called quality diversity and the huge problem that was holding it back. From there, we'll unpack the big breakthrough that made it work, check out the test results, and then finally, talk about what this all means for the future of robotics.
All right, so let's set the scene here. The biggest challenge in robotics, really, is building machines that don't just fall apart when the real world gets messy. See, most robots are programmed with just one perfect way to do something. But the second something unexpected happens, say a part gets damaged, that perfect plan is toast. To make this super clear, just picture a walking robot. What happens if one of its legs snaps, or maybe just gets stuck? A normal robot would just freeze up. Game over. So the really big question for researchers is this. How do you get a robot to figure something else out, on the fly, when its own body lets it down?
And this right here, this is the solution. It's a total shift in thinking. Instead of giving a robot one single perfect way to walk, what if you gave it an entire library of different ways to move? A whole collection of strategies that use its feet in all sorts of different ways. That way, if a leg gets damaged, no big deal. The robot just dips into its library and pulls out a new plan that works around the problem. It's not about finding the one best answer anymore, it's about having lots of good ones ready to go.
So this idea of finding many different good solutions has a name. It's a really powerful approach called quality diversity. And a great way to think about it is like you're creating a cookbook for the robot. A cookbook filled with tons of different recipes for movement that it can pull from no matter the situation.
So to get a little more formal, quality diversity, or QD for short, isn't about finding the single best solution. It's about finding a whole bunch of them. And the key is that each solution has to be high-performing, that's the quality part, and also really different from all the others, that's the diversity part. You know, this slide just nails the concept perfectly. Think about it. Traditional optimization, that's like trying to find the one single highest point on a mountain. That's your only goal. But quality diversity is totally different. It's like you're an explorer trying to map out a ton of different useful paths all over the entire mountain range. You don't just care about the summit, you want to understand the whole landscape of possibilities.
So how did these QD algorithms actually build that cookbook of behaviors? Well, this flowchart gives you the gist of it. The algorithm basically just starts trying stuff out. It samples all these potential solutions, different ways for the robot to walk or crawl or maybe even drag itself forward. It checks how well each one works and then stores the most effective and the most unique ones in a library, which they call an archive. And over time, that archive grows into that rich map of different, high-quality movements we were talking about.
Okay, quality diversity sounds like a dream come true, right? And there's this state-of-the-art algorithm for it called CMA-MAE that is amazing at it. Seriously, it's brilliant at finding new behaviors while also improving the ones it already knows. But, and it's a big but, it's got a huge problem.
Yep. For all its brilliance, CMA-MAE has a fatal flaw. And this flaw has basically made it impossible to use on the kind of complex, high-dimensional neural networks that you find inside a modern robot's brain.
And here's the flaw. Its time complexity is quadratic. Now what that means in plain English is that as the robot's brain gets more complex, the time it takes to run the algorithm just explodes. It gets exponentially slower. So if you double the complexity of the controller, the runtime might quadruple. For the thousands of parameters in today's robots, it's just painfully, unusably slow. This analogy is just perfect. It's like having a GPS app where every time you add one new city to its map, it has to recalculate the distance from that new city to every single other city it already knows. The amount of work just spirals out of control, and that computational bottleneck has been a major roadblock for years.
So how do you fix a problem that seems impossible to scale? Well, this is where the new research really shines. The scientists didn't just toss out the powerful CMA-MAE algorithm. Instead, they figured out how to make it scalable using 3 really clever approximations.
And here they are, the breakthrough. 3 new versions of the algorithm. Now, don't worry about the crazy names like LM-AMA or SEP-CMA. What's important is that each one represents a new, clever trick to get around that massive complexity problem that was killing the original.
So here's the secret sauce. The old algorithm was slow because it was trying to keep track of this super detailed, complex model of every possible solution. These new versions, they get around that by using simpler but still really effective approximations of that model. It's a shortcut, but a really smart one that gives you huge speed boosts without really losing performance.
Now, of course, a new method is only as good as its results. You gotta prove it works. So the researchers put these new guys to the test. They compared them against the old slow method and against other top algorithms on some really tough robotics challenges. Let's see how they stacked up.
Let's start with speed. And wow, just look at this chart. The original CMA-MAE chim took over 193 minutes. That's more than 3 hours. The new version, CEP CMA-MAE chim, did the exact same job in just over 4 minutes. I mean, that's not just an improvement, that's a revolution. It takes something that was totally impractical and makes it routine.
And they didn't just play around with simple problems either. They threw these new methods at some really difficult robotic challenges, like training these complex robots, the hopper and the walker. We're talking about machines whose neural networks have over 18,000 parameters.
So they're way faster, but are they actually any good? This performance chart gives us a huge yes. On this hopper task, the new variant didn't just keep up with the old state-of-the-art method, it actually beat it. It found a better, more diverse set of solutions, so you're getting more speed and better results. It's the best of both worlds.
But wait, there's more. There's one other huge win here: simplicity. The other big methods out there require researchers to fine-tune over 18 different settings, these things called hyperparameters, and it can be a total nightmare. These new CMA-MAE variants, they only need 5. That makes them not just faster and more powerful, but also way, way easier for people to actually use.
All right, so let's tie this all together. We had a powerful tool that was too slow. Then we got some clever fixes that made it fast. And we saw the amazing test results. So, what does this breakthrough actually mean for robotics going forward?
The big takeaways are really clear. These new methods are, 1, incredibly fast, 2, they are way simpler for scientists to actually use, and 3, they're what's called black box. That just means they can solve a problem without needing to know all the messy details, which makes them super versatile for all kinds of different challenges, not just walking robots.
And that's really the bottom line here. What this research does is it lowers the barrier to entry for everyone. It makes creating these diverse, adaptable, resilient robots so much faster, cheaper, and more accessible to way more people. It's basically democratizing the ability to build smarter machines.
Which leaves us with a really exciting final thought. For a long, long time, making a truly adaptable robot was this incredibly slow, expensive, and complicated challenge. Now that that barrier has been smashed, it just opens up a whole new world of possibilities. So the question isn't if we can build these amazing robots anymore. The question is, what incredible challenges are we going to solve with them next?